An open-top rectangular box is being constructed to hold a volume of 350 cubic inches. The base of the box is made from material costing 6 cents per square inch. The front of the box must be decorated and will cost 12 cents per square inch. The remainder of the sides will cost 2 cents per square inch. Find the dimensions that will minimize the cost of constructing this box. Let's first diagram the box as we see here, where the dimensions are x by y by z. And because the volume must be 350 cubic inches, we have a constraint that x times y times z must equal 350. Now before we talk about our cost function, let's talk about the surface area of the box. Because the top is open, we only have 5 faces. Let's find the area of the 5 faces that would make up the surface area. Notice the area of the front face would be x times z, which should also be the same as the area in the back, so the surface area has two xz terms. Notice the right side of the right face would have area y times z, which would be the same as the left, so the surface area contains two yz terms. And then finally the bottom has an area of x times y, and because the top is open, we only have one xy term in the surface area. And now we'll convert the surface area to the cost equation. Because the bottom costs 6 cents per square inch, where the area of the bottom is x times y, notice how for the cost function, we multiply the xy term by 6 cents. And because the front costs 12 cents per square inch, where the area of the front would be x times z, we'll multiply this xz term by 12 cents in the cost function. The remaining sides cost 2 cents per square inch, so these three areas are all multiplied by 0.02 or 2 cents. Combining like terms, we have this cost function here. But notice how we have three unknowns in this equation, so now we'll use a constraint to form a cost equation with two variables. If we solve our constraint for x by dividing both sides by yz, we can make a substitution for x into our cost function, where we can substitute this fraction here for x here and here. If we do this, we get this equation here, and if we simplify, notice how factor of z simplifies out, and here factor of y simplifies out. So for this first term, if we find this product and then move the y up, we would have 49y to the negative 1. And then for the last term, if we found this product and move the z up, we'd have plus 21z to the negative 1. So now our goal is to minimize this cost function. So for the next step, we'll find the critical points. Critical points are where the function is going to have max or min function values, and they occur where the first order partial derivatives are both equal to 0, or where either does not exist. Then once we find the critical points, we'll determine whether we have a max or a min value using our second order partial derivatives. So on this slide, we're finding both the first order and second order partial derivatives. We have to be a little careful here though, because our function is a function of y and z, not x and y like we're used to. So for the first partial with respect to y, we would differentiate with respect to y, treating z as a constant, which would give us this partial derivative here. For the first partial with respect to z, we would differentiate with respect to z and treat y as a constant, which would give us this first order partial derivative. And now using these first order partial derivatives, we can find these second order partial derivatives, where to find the second order partial with respect to y, we would differentiate this partial derivative with respect to y again, giving us this. The second partial with respect to z, we would differentiate this partial derivative with respect to z again, giving us this. Notice how it's given using a negative exponent and in fraction form. And then finally for the mixed partial, or the second order partial with respect to y and then z, we would differentiate this partial with respect to z, which notice how would just give us 0.04. So now we're going to set the first order partial derivatives equal to 0 and solve as a system of equations. So here are the first order partials set equal to 0. This is a fairly involved system of equations which we'll solve using substitution. So I decided to solve the first equation here for z. So I added this term to both sides of the equation and then divided by 0.04, giving us this value here for z. But if we find this quotient and move y to the negative 2 to the denominator, we can also write z as this fraction here. Now that we know z is equal to this fraction, we can substitute this for z into the second equation here, which is what we see here. But notice how this is raised to the exponent of negative 2. So this would be 1,225 to the negative 2 divided by y to the negative 4. So we can take the reciprocal, which would give us y to the fourth divided by 1,500,625, and here's the 21. Now that we have an equation with just one variable y, we want to solve this for y. So for the first step, there is a common factor of y. So y equals 0 would satisfy this equation and would be a critical point, but we know we're not going to have a dimension of 0, so we'll just ignore that value and set this expression here equal to 0 and solve, which is what we see here. So we're going to isolate the y cubed term and then cube root both sides of the equation. So if we add this fraction to both sides of the equation and then change the order of the equation, this is what we would have. And now from here, to isolate y cubed, we have to multiply by the reciprocal of this fraction here. So notice how the left side simplifies to just y cubed, and this product here is approximately this value here. So now to solve for y, we would cube root both sides of the equation, or raise both sides of the equation to the 1/3 power, and this gives us y is approximately 14.1918. And now to find the z-coordinate of the critical point, we can use this equation here where z is equal to 1,225 divided by y squared, which gives us z is approximately 6.0822. We don't need it right now, but I went ahead and found the corresponding x value as well using our volume formula solve for x. So x would be approximately 4.0548. Because we only have one critical point, we can probably assume this point is going to minimize the cost function, but to verify this, we'll go ahead and use the critical point and the second order partial derivatives just to make sure. Meaning we'll use this formula here for d and the values of the second order partial derivatives to determine whether we have a relative max or min at this critical point when y is approximately 14.19 and z is approximately 6.08. Here are the second order partials that we found earlier. So we'll be substituting this value for y and this value for z into these second order partials. We should be a little careful though, because remember, we have a function of y and z, not x and y like we normally would. So these x's would be these y's, and these y's would be these z's. So the second order partial with respect to y is here. The second order partial with respect to z is here. Here's the mixed partial squared. Notice how it comes out to a positive value. So if d is positive, and so is the second partial with respect to y, looking at our notes here, that means we have a relative minimum at our critical point. And therefore, these are the dimensions that would minimize the cost of our box. This was the x-coordinate from the previous slide. Here's the y-coordinate, and here's the z-coordinate, which again are the dimensions of our box. So the front width would be x, which is approximately 4.05 inches. The depth would be y, which is approximately 14.19 inches. And the height would be z, which is approximately 6.08 inches. Let's finish by looking at our cost function, where we have the cost function in terms of y and z. In 3 dimensions, this would be the surface, where these lower axes would be the y and z axis, and the cost would be along the vertical axis. We can see there's a low point here, and that occurred at our critical point that we found. I hope you found this helpful.